is actually something like a wave, which is sort of wobbling around in some potential with which I trap it. So it is very much like transporting some liquid, okay? And if I want to transport some liquid from here to there, let's say that today Enrique invited me, and of course there is limited time, so he gave me like 1 hour for speaking. But I have things which I want to tell you, which is for 4 hours. So I would like for him not to realize when 1 hour has passed. So I need to get him drunk, okay? I hope that he likes champagne, and here I have a source of champagne, which is very cold and pleasant, okay? I just put it in my glasses, okay? I fill my glasses to the brim, I have to deliver it to him. And then, what can I do? I want to deliver to maximize the amount of champagne that he will drink, so I can, physically, I can transport this adiabatically. Okay, adiabatically means without having any excitation, so I will very, very slowly do this. After a long time, I will get here, but there is a problem, because I cannot take all the time that I want for quantum processes, because there is the need to preserve quantum coherence. So the interaction with the environment, okay, will heat up my system. The champagne will be warm. It will not be, agreeable, and so he will not drink it. So what I can do, of course, is I can obviously try to restart, and then, I will do this with some sort of linear time dependence. I will do it like this. But of course, if I do this, I have non-adiabatic transitions in the sense that my glasses will fall to the ground, and so my fidelity will also fall to the ground. So what I can do is, and this is obvious to all of you, of course, I use all my control parameters. I will tilt my cup. I will come there, and I will serve. So in quantum terms, it means I am exciting my system to a higher energy state, and then I have to use quantum interference to go, which is something exquisitely quantum, the fact that, quantum states, they combine linearly. So the final state, if I excite more than one state, the final state will correspond to the evolution of all these different initial states, and this will happen with certain phases. And I can choose the phases such that in the end, I just serve my atom the state in which I want it. So I have to do it iteratively, and of course, I have to be able to simulate. So here is where all the knowledge that I can have. Can I build a digital twin? And nowadays you say digital twin, but actually it's a model. The best I can model my system, the better I will be able to speed up my process, okay? And this is something which, is not typical physical processes, as much as this picture is not a typical physical picture, but, it exists, and that's what we have to find, and there is a very tiny chance to find it, because the precision we need is really the maximum that you can get. Otherwise, we will never be able to make quantum computers. This is going to really make the difference between can we make it scalable with a high number of qubits or not. And then, of course, you have to use all of your control parameters, and then we try to play some more interesting games. In the quantum domain, so this was, of course, classical. In the quantum domain, what happens is that I have some discrete energy levels. They depend on time. And so let's assume that I want to, maybe I have a many-body system, so several quantum bits which I want to move into a large entangled state, a state in which I have a superposition of all possibilities, which will correspond to all possibilities, all computational paths in a computer. So, of course, if I want to go from one phase to another phase, what I can do is, again, I do it adiabatically, means I don't want to excite my system, I want to go slowly to stay close to the lowest energy state. And then if I go slowly, okay, at some point maybe I will have a little bit of a deviation, but I will stay close there, and I will generate the system state that I want. But then, of course, if I shrink, then what happens? So there is a famous problem that in here, there is a Russian guy, his name is Landau. So this is a so-called Landau-Zener crossing, meaning that if I try to do an evolution through such a system which has these energy levels, since here there is a gap which is closing in my levels, then what will happen if I go fast without optimization, I will excite my system. But this is exactly what I wanted, because I said I want to excite my system in the beginning and then de-excite it. So if I can use it properly, and of course I can do that with control methods, when I optimize, I excite even more perhaps, but then this quantum interference, okay, the combination of different states with given phases in a coherent way will make it such that I get to the goal in a shorter time. And here is a first example of that, how I do this in a very simple physical process. So I have a chain of spins, okay, which could be atoms, electrons, and then I have, here is this superposition state. the fact that, you know, in a quantum bit I can have 0 and 1 at the same time coherently summed. It means I am with, you know, in this system with a certain probability amplitude in state 0 and another probability amplitude in state 1, and everybody else is in state 0, and then in the end I want to move this initial state to the other end of the chain. And this is relevant for instance, you know, processors, part of a quantum processor in which I have different quantum states, and I have a wire connecting them in order to move this state from one point to the other. And there has been a proposal more than 20 years ago how to do this in the following way. So here is the Hamiltonian that we write. So this is a quantum Hamiltonian for spin-spin interaction, okay? Interaction between the spins, the angular momenta of these atoms or electrons. And then I can have an external control parameter, so I can have a magnetic field which is non-homogeneous, so it will have a minimum around you know, the left end of the chain here in the beginning. I can change its position, I can change its intensity, and I can go through, and what I want to do is to change it in such a way that the spin gets transferred. The reason why it can work is that next to the minimum, okay, the spins can swap, can exchange their angular momentum due to laws of physics. So if I move that, it's like transporting one particle, okay, from one point to the other. And now I have to see how I can play with the intensity here and with the distance in order to achieve that either adiabatically, as I said before, very slowly, or to accelerate this. So if I try to do this slowly, it just means that I move step by step. I wait, okay, I move it, I wait that my first spin swaps to the second one, and then step after step, I get to the end. But again, this is something which goes slowly. I want to speed it up. If I speed it up in a way which is not optimized, what I have is I have these Landau-Zener crossings such that at each step, I leave a little bit of spin behind. In the end, I get half of my qubits in the, I have a 50% probability, or less even, that I get to the final state. So if I optimize, well, then there is, fortunately, okay, so there is not only evil Russians such as Landau, okay, which you know, is there preventing the thing for going in a good way, but there is an important theorem I want to, and maybe it is also in your field, but in physics, there is a theorem. Given any problem in theoretical or experimental physics, there exists a Russian who solved it 40 years ago. And a relative or pupil of said Russian will stand up during or after the seminar and will tell you, we do this in elementary school. And it is actually, the fact is, it's a theorem, so it's actually true, okay? The fact that this is true also in this case was proven by the fact that said Russian, whose name is Krotov, okay? Mr. Krotov, after I gave this talk, the first part of this talk, plus more sort of non-technical details for the public, in front of 15 million viewers on Russian television, it was like 10 years ago, I like to remind my Italian colleagues that this is 50% more than Fiorello in Festival di Sanremo, okay? So he called me and thanked me for advertisement. So it is proof that he actually exists, the theorem is fulfilled. So given, you just have to pick the Russian which does it for you. In this case, the name is Krotov, use Krotov algorithm. And the way we do this is, you know, it's by forward and back propagation. And actually, this is someone from really your community, I would say, because he was from the Institute of Aeronautics and Control of the Russian Academy of Sciences. So, and what happened was some colleagues just ported his algorithm, backward and forward propagation, into quantum domain. And what it does is simply,
so then once again they were doing quantum control much before in Western we knew
exactly
still existed, right?
Exactly.
When was this?
So his papers were in the 70s, in the beginning of the 70s. So really, like actually,
the papers by Rabitz and so on are the late 80s, right?
Exactly. So Rabitz and co-workers, they took it. Actually, David Tannor, for instance, a colleague of Rabitz, now from the Weizmann Institute, he really developed a quantum version of the Krotov algorithm, and also Ronnie Kozlov, some other colleagues, which were doing that. And essentially what it does is, no surprise, with iteration, it changes the time dependence, of course, of the intensity and of the deviation from a linear slope.
Krotov did it for an Schrödinger-like model, or he was thinking on a classical
So Krotov was doing it for a classical aeronautic. He never worked, or only late, he has one paper on quantum, and it is the colleagues Tanner and Kozlov which just used this and applied it onto where the dynamical system, they replaced the dynamical system plane with the dynamical system Schrödinger equation, essentially. And so it was a breakthrough for our community in terms of the ability to use this, but it was not a breakthrough in terms of developing the ideas, because all the ideas were already contained originally, because it's anyway PDEs, and so this is really your bread and butter somehow. And so when you have this, of course, you have in the beginning, you have this excitation, and then the excitation, which works as follows. In the beginning, you delocalize, you start juggling your spins, you delocalize, it's like a moving soliton, and then you catch them all back by quantum interference with a high fidelity in a time which is a couple of orders of magnitude shorter than what would be otherwise.
What happens in this flat intermediate stage? You seem to have a very singular action in the beginning and in the end, and
yes.
in the middle it looks flatter.
You are accompanying it because you are, so let me try to go back. So what happens in the flat intermediate stage is first you have excited, and then you have this sort of delocalized thing. You are accompanying it while it is going forward, and then you de-excite it. So you have given it some momentum in the beginning.
More like the adiabatic strategy.
No, well, it's one could say like locally adiabatic, okay, because the excitation gives also a momentum, so the thing starts moving, and it moves. Of course, it would delocalize in a different way, so you have to just accompany the movement and keep it a little bit together, like cat herding, and then only in the end you have to stop it, okay, and then the excite.
You enter the wave, then you are driven by the wave.
Yes, and you stay in equilibrium, and then you quit. Absolutely, yeah, it's really like surfing. Yes, absolutely. So this is something which then works mathematically, but you have to be, it's not very robust, you have to follow very precisely this pulse shape, and so you start, and then if you do it for kind of more realistic systems than just a spin chain in a lab, then there will be non-idealities, there will be issues, of course, in the way in which you realize it in practice, so you need for it to be more robust. Also, you need for it to be more efficient, because here there were hundreds of iterations, but when you do it in an experiment, doing this quantum experiment, it takes time. They need to repeat it to get the proper statistics and so on. So it's not, you cannot have like thousands of iterations for doing that. So you want something more efficient. And so this is why we invented, and this was still when I was in Ulm, this algorithm, the chopped random basis CRAB algorithm, which I will explain in a moment how it works, because then you can use it also for other applications in quantum computing. The work that we did with Danny Burger here was about something similar, but now not transporting one qubit, but just manipulating one end of a chain in order to realize any arbitrary quantum operation between any two elements of that chain. So, but now what I want to do is really going towards how we use this CRAB, starting from an initial pulse shape. So the idea is that you update the pulse, multiplying it by a certain function, which is just very simplified. So you simplify your search space, and you just write your update factor as a function of a few basis functions, okay? And you just look for the amplitude of that. And it could be sinusoids, it could be other polynomials. And there needs to be a little bit of random component here, because then what you can do with this is this leads to dimension reduction. So you have your landscape, which is depending only on a few parameters. And then you can use even some simplex search to just go down the path. And the advantage of this is the pulse that I get in the end is something which has some pre-specified spectral features which can be realized in an actual experiment. So I can go to the experimentalist, they tell me, okay, here is my pulse modulator, this is what I can do, and then we synthesize a pulse which works for them. And the randomization is there also because along the path you could get into some local minima, and then you want actually to escape from that. I have a slide on that in a moment. So this is and of course you could use other ideas. So simplex search is one. So Nelder-Mead kind of algorithm. You can use other sort of conjugate gradient methods. You can use swarm ideas, evolutionary algorithms you can use nowadays. I mean, anything which is on the machine learning toolbox. Still, when you are trying to push this, so the landscape, when you're trying to push it to the limits, this landscape becomes physically more and more jagged and more complex. So you have more and more local minima, and you have to sometimes escape them in a non-trivial way, and just randomizing maybe not enough. So we developed, so we called it dressed crab, okay? We developed this new version of this, which means if I am in a local minimum, since my landscape here is dictated by the way in which I cut my expansion in the function, I just remove one of the basis functions and I put a new one, okay? Just one of the components, and then suddenly my landscape becomes different, and I have a probability close to 1 that now I will no longer be in a local minimum, and I can escape that and go down to the actually closer to the global minimum. Yeah. So this is something in which I can use to accelerate this process to get to the goal with less iterations in an actual experiment. Another thing which we use, so as I said before, you can use Fourier basis, as I said before, you can use a sync basis. Also, since in many cases for quantum processes you have to switch on and off something, also a sigmoid basis can be very useful. They have different spectral properties, and sigmoid, for instance, has less leakage outside of a certain cutoff space, and so on. So this is something that we, actually it's no longer in preparation, this is a paper which appeared a few months ago. And you can see that depending on different problems, okay, you can get different bases working better. So in this case, for instance, for a single qubit gate, sigmoid basis outperforms the other ones. If you want to go for a 2-qubit gate, then, as a matter of fact, it is the sync basis which is better. So you can develop, adaptive algorithm in a very practical way, which enable you to do the standard operations which you have in a quantum computer. Also, you can go beyond what is sort of standard, in the sense that you now do, instead for qubits, you do gates for qubits. And also here you can compare what happens with a piecewise function and with a smoother function, and so on and so forth. Nothing which would be surprising to you, but somehow things that we need to adapt to real experimental systems. So in the end, what we get is that we have our experiment, or something which is simulating it, and then our algorithm can optimize it just by even treating it as a black box. Okay, so you have this experiment, you get some figure of merit measured, you apply a pulse, and you don't even have to be able to compute the pulse, because this can even be done over the cloud, in a sense, can be done remotely. And so this is where we developed methods to do that. So now in the last, how much time do you have?
Sorry,
yes.
Tommaso,
yes.
When you say pulse, it gives the impression that control actions are like kicks.
Oh, no.
Direct delta.
Thank you. When I call pulse for me is any shape. So actually, I talk about pulse shapes. So and it's a very important language point. Yes, absolutely. And the point is for it to be smooth and to be feasible. And let's see. For instance, the first time that so now I go a little bit. Do I have 20 minutes still? Okay, very good. So I will give. So this was about the methods, okay? And I will give a little bit a few examples how they work in practice. So this was the first example in which you applied it to a single qubit gate on some color centers in diamond. The point is you address them with some laser, you read out the fidelity of your operation, and you iterate. And here you see why the student can go home, because at midnight the fidelity is less than 50%. Tomorrow morning at 8, the thing is automatically gone to 100%. Okay, and with no human interaction, and it works. So we developed even an open access software suite. We have different types of evaluation metrics which you can implement in there, for different. I will not go into details of that, but which are suited for specific, physical features of this system. And now we can finally go to the points in which we take this and we apply it to the building blocks of making a quantum computer with atoms. So if you want to make a quantum computer with atoms, you need very cold atoms because they have to be coherent. So first of all, you have to cool them. And what we did here is we wanted to test that it really works via cloud. So we used an API which was developed by our colleague Jakob Scherson in Aarhus in the context of a citizen science experiment, in the sense that there were people, like real people, not physicists, which were connecting to their website. They would get this video in which you see that there is, this hot fluid of atoms, which then gets, poured in a very disorderly way into a cup which is made out of lasers. And this cup, which is made out of lasers, then you lower the cup, and then the most energetic atoms disappear until the atoms get very, very cold, okay? And then you get, here is the real experiment, in which you start with atoms, you transport them into a trap, in which you can tune the depth, the intensity of those lasers, and you can do that with a graphical interface in such a way that, real people can play with these pulse shapes, and the reward that they get, so they get the prize, the winner is the one who manages to make the most atoms ending up in this very cold quantum state. And so this is relevant because in the end, what you can get is there are different strategies to do that. You can lower first one laser and then the others. You can lower the magnetic field and so on and so forth. And these are typically, connected in, first you start with a wide trap and then you close it, or vice versa. There are also, different strategies which humans find. And humans can also find bridges in between, so the different protocols based on intuition.
There is no one optimal control theory telling what is the optimal strategy ever, no?
That's right, exactly. That's.
Why there is not a theory? Is because there is not a clear mathematical model for this?
Because there is not a univocal mathematical model, and because the mathematical model would be, first of all, because it is an open system, so it involves noise, because there is cooling, okay? And second, because anyway, calculating it's millions of atoms in there, so one could do things analytically, but only in principle, because these systems are too complex to be simulated. Okay, but the point here was that the goal of these people doing it with people, doing it with the humans, was sort of to see how humans would explore this and so on and so forth. For us, what was relevant was to see whether we managed to get something which actually works over the cloud. And then interestingly, so what I find interesting is not that our algorithm outperforms people, but actually that it outperforms people just by 10 or 20%, because actually people can get really the very good results out of there. But for us, the important point was, you have your experiment here, and our algorithm is sitting in Jülich, in our research center, and then you can optimize via the cloud. So we can even sell it as a software, cloud service in a sense. And of course, you can start applying machine learning in the sense that, of course, a neural network can learn your landscape, okay, based on a certain quantum system. So here is, an example of a certain path that we have. Then there is the quantum time evolution, which you realize as a quantum circuit like this, and then you can learn this with a surrogate model, which you develop via machine learning, and this can also be used for you then to move forward. And once you have your atoms in this cold state, then the next thing you want to do is you want to load them in a quantum register. So one atom per lattice site in a certain regular lattice structure. The way it works is, okay, here is my cold cloud of atoms, okay, which have a certain density, and here is a field which I create, a potential for the atoms, which can trap one atom per lattice site. So this is an optical lattice done with interfering laser beams. I can raise the depth of this potential or the intensity of the lasers in such a way that I will end up with one atom per lattice site. I want to suppress defects in which I have two atoms in one point and zero on the other side. And people have been optimizing in the last 20 years, okay? They have been optimizing this, and they can do this in sort of a few hundreds of milliseconds. And our point was we wanted to do in a much shorter time scale, in the sense that, here is the yellow curve is what they did after like 20 years of trial and error. We wanted to do it much faster. Of course, if we do it much faster without optimization, like in a linear way, then we don't expect a good result, and our optimization algorithm will be able to, and again, this is the pulse shape, okay, smooth, but it's not something that you can do analytically, okay? You really have to iterate with your system. And here is the result. So you want in the end to have, so the one means the density of atoms inside the inner region of this lattice. So I need one atom per lattice site, so it should be flat, this curve up here. If I do it, you know, without optimization, I get 15-20% of defects like empty sites and double atoms. And instead, if I optimize with my algorithm, I can get it 1 per lattice site. And the point is, I can do this in the shortest possible time. Because, you know, of course, if I try to do it shorter and shorter, then at some point I will no longer be able. So here's the error that I do. If time is long enough, I have low enough error below a certain, you know, uncertainty noise floor that they have in this experiment. If I try to do it too fast, shorter time, then I get, you know, an error which is equal to essentially 100%. And I can tell the experimentalists at which time they can do this in a way which is compatible with their noise. And this is something which they would not be able to do if they just did it with their standard processes. So I'm able, yes?
When you show these pictures in which, you know, the trajectories go up or higher in energy and then to go down,
yes,
and so on, are the control strategies employed for generating these strategies more and more impulsional, more and more concentrated on timeline or not?
No, not they are more concentrated in time because the time scale is shorter.
Yeah.
But no, it's not. It's not just a pulse. Not just a kick and that's it. No, it has to work in continuous time. Yeah, that's one of the challenges. Otherwise, it would be much easier to simulate. Okay, so once you have this, you have your atoms. They are cold. They are sitting one per site. So I have my qubits. Now I want to move them around. Okay, to perform my quantum gates. So here is where I do my transport of atoms with some fast experiment in which I have, so here I have to have, you know, my qubit states, my quantum states 0 and 1, they correspond to internal states of atoms, different states in which electrons in the atom are in different internal states, so, like we see in chemistry, like S and P states, whatever, you know, different electronic states. And I can realize an experiment in which, you know, I move these atoms depending on their internal state. If the atom is in a certain state, red state, let's say, it stays here. If it is in the blue state, it moves around. This is an experiment which they did in Bonn. And this is how they can very precisely control, again, you know, these kicks, as we said before, are sort of not just simple, but always a little smooth, while I am making the time shorter and shorter to transport my atom from one point to another in this situation. And here is the final plot of the fidelity that I get. I would like for it to be always 100%. Here is as a function of time. For long times, okay, I'm just doing what I said before. So I'm going slowly, okay, and transporting my atoms slowly, and then I get to the goal. But if I, you know, shorten the time, at some point with a non-optimized pulse shape, which here I also call ramp, you know, in the end, the fidelity will go down. Only if I optimize, and these are measured results, I will be able to get to the speed limit, so the minimum possible time by which I can still get unit fidelity for time which is much shorter than this adiabatic time scale. Okay? And if I do this now in a state-dependent way, like I take, as I said before, my red atom stays here, my blue atom goes back and forth, and I can check that actually it comes back, so it was here, and it was in a coherent superposition, so the quantum properties of the state are preserved. But when it is here in the middle, it's in a superposition of red state, like down, like 0, left, and blue state, like up, like 1, right. So it is really this small Schrödinger cat, this superposition of one atom here and there at the same time. And I can do this, again, with optimization in a time which is short and short and short, even you know, for times which otherwise, if I didn't do optimization, I mean, I would already be completely dead. I would have, you know, a lot of error down here already if I didn't use these control methods. So in the end, I can move my atoms around. I want also to make many of them in a quantum state, a so-called entangled state, which is the one which is used for quantum computation. So this is a fat Schrödinger cat. So I want to make atoms the largest possible number in such a superposition state. For this, we used a machine. This was already a few years ago. We used a machine which then was spun off from Harvard and MIT into a startup, which is now one of the world-leading startups for making quantum computers. They are using atoms. They are taking these atoms in optical tweezers, so really like laser fields which trap their atoms one by one, and then they put them in a regular array. they can control, globally with some laser fields, with frequency and intensity of this laser, they can change the frequency and intensity of the laser for going from an initial state in which all the atoms are in 0 to a final state in which the atoms are in this highly entangled state in which they are 0, 1, 0, 1, 0, 1, plus, at the same time, 1, 0, 1, 0, 1, 0. So two very different states of up to, in this case, 20 atoms. So these 20 atoms are at the same time in one state and in a completely different state, all of them. So this is what is named a Schrödinger cat, and here is how we did it. Again, our pulse shape, okay, is somehow smooth for the frequency and for the intensity of the laser, and in the end, what we get is we go on the other side of this transition, having, the two possibilities, up, down, and down, up, and they still are coherent in the sense that I can do an interferometry experiment, which is showing me, with these oscillations here, that these guys are really in a quantum state, and not just either or, but both at the same time. And I can check that with increasing number of atoms. So this signal here is telling me if I have these oscillations, I know that there is quantum coherence, that they are in both states at the same time. It has to be the largest possible oscillation, so if they become too small, then it's no longer this quantum superposition. So this is the largest we could get, the number of 20 atoms, which can be brought with this control into a state which has a fidelity of more than 50% for being essentially in this entangled state. And if I don't do the optimization, I would be below 50%. So this is really the situation in which I can say that with this optimal control, I'm not only doing things faster, but I am doing something possible, making something possible, which would be impossible otherwise. And here is a picture of what happens when I increase the number of atoms from 12 to 20. And what I said before, I am exciting, I have to excite and de-excite. So during the process, here below is the fraction of atoms of the atom population which gets excited into some state which is not the ground state of my system, not the lowest energy state. And you see that as the number of atoms increases, I have to go further and further away from this ground state, because only in this way I'm able to achieve this result. So now I can do all the building blocks. I can put my atoms, I can cool them, I can put them one by one in my register, I can move them around, I can entangle them. I also want to go a little bit higher in the stack, as I said before, so I want to compile sequences of gates. This is the last part of my talk, so I'm almost finished. And the point is, when I want to do a certain algorithms, it depends on which gates I use to decompose it. If I use as standard, in standard way it is done, I use some, certain 2-qubit control NOT gates, so-called. It is this one. And, T gates, individual qubit gates, and so on. I need, if I restrict the number of gates that I can, the set of gates that I can use, I need a high number of those in order to realize my algorithm. And this means more time, it means more decoherence, it means more errors. So I want to make a shorter circuit. I can simplify the circuit and compile it in a simpler form if I use some continuous gate set, like a parameterized family of gates, and I need to synthesize these parameterized gates in order to work in a flexible way. So this is what we do, again, using machine learning, in the sense that we can start with a large parameter space, okay, with all different possible parameters, and I want always the best possible gate for all the possible values of this parameter, and I can do this either in a supervised learning mode, like I optimize this for each value of the parameter, and then I get the optimal data, and then I feed this into a neural network, which will learn what is the best overall pulse shape, or I could do this with a different directly feeding all the parameters into a network and optimizing globally, okay? This is what we call, it's based on backpropagation. This is what we call SOMA in the sense of single optimization. We optimize once, and we apply it in multiple instances, and in this way, I can get something which works for what? For instance, in a processor, in this case, it is a processor of the type which Google has, so with superconductors, with different superconducting circuits instead of atoms for my qubits, and every time I need to have a slightly different parameter here so that I can address individual qubits in this problem, and I want one way which works for all of them. So I need to have this variability and optimize for that. Or another case in which I need variability is when I have my parameters in my system drifting with time, which normally would require extensive calibration and recalibrating every time, but in fact, I can do an optimization which takes into account the fact that I can have this range of variability and still produce some quantum gate which works with very high fidelity. Here's an example, again, a single qubit gate, a simple example over a large sample of different parameters, and here you see that we get even 3 orders of magnitude improvement using this machine learning method with this sort of global optimization with backpropagation as opposed to what we get in simple terms without using these methods. So I'm at the end of my 45 minutes, and what I told you is the library of methods that we are expanding, and we are always working into sort of going further, and this is why it is so interesting for me to talk to experts in the field so that I can learn more. I showed you how we can use this for the different components of this, how we can make the fastest and biggest possible entangled states, and also how we can scale it up the stack by bringing together and piecing together different gates and synthesizing gate sequences in terms of compilation. And, well, this is all I had to say for you today. Thank you so much.
Thank you, Tommaso, for this extraordinary talk. So, questions and comments? Yes, Lorenzo.
Well, 2 things actually. For this question part, it would be best if you take away your mic
Oh.
and we give it to
Oh, yes, sure.
asking the question and then
Makes a lot of sense. Yes,
for
yes,
3
yes.
reasons, sorry.
Sure, sure.
But I actually have a question.
There you go.
So, okay, thank you. My question is to make Professor Dodua and Professor Gugat proud. Gugat has gone, probably. But are you familiar with the concept of turnpike? Because I think this is also related to some of the question that the professor was asking you before. Is this idea in control theory where like the optimal control is made of 3 parts. Like the first one, you go to the control for the steady state, basically, and then you stay on the control of the steady state, and then you exit on the last part, right? And seeing some of your pictures reminded me of this. So I don't know if you're familiar with it or not, and if it applies to these kind of systems.
I think it does apply. So it came up in discussions with control experts like your community. Several people have pointed out that this is something which seems to be emerging here. We have not sort of gone more in depth into this in the sense of checking whether this sort of could be applied in a systematic way for these kind of things, and it might be indeed one interesting direction for that. Thank you.
Other questions or comments? I think Giovanni is there. So we organize.
Thanks, making it up. I come to the front. So. My question is probably
The professor
probably due to my being new to this field and maybe not have understood what you were trying to say, but did I get it correctly that essentially you want to do an operation with these qubits, and then for every new operation you need a new control, right? And so the question is then, can you do it on the fly, or do you have to pre-compute all of these controls and then somehow build your computer from pre-computed things? So what happens if I have a new algorithm that I want to design?
Thank you. That's a very important question. I should have clarified it better, evidently. So the goal is indeed to synthesize, so pre-identify what would be the best pulse shape to realize a certain set of quantum operations, so that compilation will mean I have my algorithm, I know which operations I need to do when, and then for each one of them I apply without recomputing it my pulse shape. However, the last part that I showed was that indeed, physically, as parameters change, or as there is some noise, or homogeneous broadening, or different aspects, in principle, this would not be so good as it would be calibrating every single gate every time you do it, but this is of course impossible because it would break everything. And so that's the reason why in the last part we are really optimizing sort of in a, you could say, fault-tolerant or noise-resistant way, in the sense that you optimize for a broad range of parameters. This was what was on the x-axis, the sample size in the end, because what we would like to have is something which is as robust as possible, and I do not need to calibrate it every time. Of course, there will be some trade-off, because if the range of parameters of the system, changes too drastically, I have to readjust. And so one point is, how do I find a proper trade-off between not calibrating too often, also not calibrating too seldom, so that I get a consistently high fidelity. That's one of the aspects of, engineering and system integration in this whole type of systems.
Questions? If you don't ask questions, I also have one. So, I mean, do you have a question? Sorry.
No, please.
Okay. No, I was actually interested if you could expand on the last something you showed on the last slide, where you have this network that basically optimizes globally. It wasn't really clear to me what is happening there and why it performs better than supervised learning.
Yes. So, well, intuitively, essentially, the point is that supervised learning is telling you, individual instances. Okay. So essentially, it can only learn from what the system does in every individual case. But what we want, in the end, according to the question that was asked before, is not necessarily that our system performs best in each individual case, but we want that, you could say, on average, okay? So actually, yes, on average, or like the minimum over all possibilities, that's what's interesting. And it is not, this is something which you can learn more directly by asking this question, so having as a figure of merit in the end, as a reward, if you wish, okay? So it is a reinforcement learning, but not supervising in the sense of, starting with something already fed in. And this, in the end, may allow you to be more tolerant. And this is actually, this was the research question for us, because we were not sure. But what turns out to be the case is that, indeed, that is more productive.
So the algorithm there is reinforcement learning?
Yes.
Okay.
Yeah. Some other question?
Again, a very basic one. This is all what one would call open loop control. There's no feedback, and the reason why there's no feedback is that you can't measure, because otherwise you would change your system, right?
Yes. That is very true. So this is one important language difference between us, quantum control theorists, and you, actual real control theorists, because what we call closed loop, okay, is not really closed loop. So we call closed loop something which is, I do the experiment, I measure, I come back, and based on the result of the measurement, I iterate, and in control theory terms, this is not closed loop. Okay, so that exactly. We call it closed loop simply because in our sort of very pedestrian world, it kind of you let the machine run, and you do not go you are not intervening. However, indeed, for the reason that you have said, so there exists actually real quantum feedback loop controls, but they cannot be based on optimization. They're based on sort of adaptive adjustments, so to say, via coherent methods, but they cannot be based on optimization, because optimization requires actually a classical computation. Unless, of course, but this is really too futuristic to be sort of practically possible to speak about that, unless you have a whole thing in which, in the loop, there is a quantum computer which is actually observing and then adapting and then recalculating in real time. But of course, this is something which sort of can be conceived, but has no practical meaning whatsoever in this moment.
Yeah, I think this is very much related to model predictive control, right? So I think model predictive control was precisely built to deal with deviations due to model errors or noise, right? And then ideally, if you will know the model, then you will have a feedback control. but because there is noise, you have to recheck again and again. And then somehow you have a semi-feedback control because, you know, it's feedback, but there is a, you know, a transition time that you have to repeat and again and again, and there is some profile. So that's, yeah, that's very interesting from, of course, I'm not sure that the mathematical theory is very clear on when somehow the level of noise destroys the performance of. Of course, all mathematical statements are about, you know, given a nonlinearity with global ellipses, constant, assuming the noise is below a given threshold, then the time has to be long, there is the control time, the implementation time, everything is kind of asymptotic, no, not very quantitative to really, and I suppose here you are facing with these limits in which the validity of the theorem is almost lost, right?
Yes, and one problem we have is that for us noise, we have very many different kinds of noise. One is noise, the way you treat it in terms of the classical controls. But for us, a very important and often the most important source of noise is quantum noise in the sense of interaction with an environment which entangles my system with the environment, but I do not control the environment, so I have to average over it. And this can happen in a number of ways, depending on for how long the information from the system stays in the environment. Because if it is immediately lost, this is a so-called Markovian system, quantum Markovian system, and you know, in this case, you only have degradation of the performance if you have that kind of noise. But there are also types of noise in which you have a non-Markovian system, in which the memory of the noise stays in the environment, memory of the evolution stays in the environment, and you can even get it back. We even had, I didn't show it here, a paper on physical review letters a few years ago, in which we showed that in a non-Markovian system, I can even cool just by control an individual system just in contact with an individual bath, because the memory enables me to take into account and to optimize for, you know, sort of getting my system colder than the bath which is around. So this is telling us that really there is a much diverse and more complex type of noise in quantum systems, which makes it, I mean, even a full systematic theory of non-Markovian systems is something which people are trying to develop now. So
for you, non-Markovian is easier to control or harder to control?
It's easier to understand and to describe and harder to control.
Okay. Yeah. So this typically for classical mechanical systems, all these and PDs, memory, of course, is a drawback, right? Because everything you do on real time will be destroyed by this cue that is coming from the past and that you don't see. Yeah.
Yes, but in quantum terms, sometimes, if the memory is not destroyed immediately, there is still some coherence lurking in the environment, okay, which you, if you are fast enough, you can catch back, okay. So it's not so. That's why we don't have sort of some nice ellipse which tells us, okay, now here it converges or otherwise it diverges.
So thank you. This is a passionate discussion. Maybe we can continue. We have a fantastic restaurant here called Mensa. Yeah, and then we can meet there and continue the discussion. But before we finish, so this is more or less a community of mathematicians or quasi-mathematicians, all of us. What will be, and many of them are young people. So I think this is a fantastic topic for people to jump in, or at least develop some interest and then get inspired on the problems appearing in this field to continue with their, you know, more theoretical research. What will be your recommendation for people interested? I know also there is online people working in Bilbao, in companies. They are very much interested on the quantum strategy at the technological and industrial level. I know also you have been a pioneer on this field. Your quantum manifesto has also pushed this, say, more technological and industrial agenda. What will be your recommendation to the two communities? One, the one that is doing more pure research at the university, and the other one that is working in companies, in computer science, informatics companies, and that now have interest on developing an activity and an antenna in quantum-oriented.
So I would say that, so the first step really, I think, should be to, to meet and exchange and sort of develop a mutual understanding, which requires a little bit of translation, but not so much actually, because we speak largely the same language. And so one thing which I may propose, because initially I was thinking that after this talk I would invite you, of course, for a colloquium in Jülich. But I am wondering whether it might make sense to not just reduce it to a colloquium, but perhaps have a small workshop in which some of my people tell you more in detail what we are doing, and some of your people tell us what you are doing. And in terms of the academic and industrial communities, so there are some very specific things which now are happening. There is this new priority on quantum computing in the high-tech agenda Deutschland. And there is a discussion about how to realize that, including in calls. And also on the European Commission level, I just got this morning a draft of a call which the Commission wants to do for middleware. And my advice to them was it should not include just middleware in the sense of taking some hardware agnostic level and compiling, but it should also involve some control firmware. And so I'm saying this because there are and there can be opportunities for funded cooperation, and it is very clearly an intention both at the national and European level to have more exchange and more sort of involvement of those communities more in the, say, mathematics and or engineering side, okay? I'm thinking, for instance, of the group of Andreas Kugi at the University of Vienna, who is doing more on the engineering side. So they have a lot of robots and machines and things, but they use a lot of very advanced mathematics. And what I'm thinking is that some sort of really interdisciplinary discussion could not only be interesting scientifically, but also practically, because now, new opportunities are coming, and there is not only an opportunity for us scientists, because what we want is funding for our research, but also from the funding agency, it's an opportunity because what they want is actually some competent people to reach with their funding. So, really these things can really come together. And one thing which would make sense, possibly, is to have a little bit of maybe a 1 day or a couple days workshop in which there is some exchange of really, and see common language. And from there, one can see in the next wave of calls for proposals, which is about to be launched, actually, next year, whether there can be some opportunities for that.
So, as you know, we are a non-profit team, right? But still, we can apply for grants, right? And so on the other hand, the applied math community nowadays is very excited by machine learning and neural networks and the training. And of course, for this, there are some flagships like large language models that we all know. We have them on our pockets. But also other very visual things like humanoid robots, right? And then the fact that generative AI has to adapt in order to deal not only with static images, but also with robot motion and so on. Is quantum, do you see quantum somehow connected with these other challenges, or is it a completely different world?
So this is an interesting question and a very timely one, because a few months ago, I have been coordinating a group of colleagues from the quantum and the AI community, and we have written a white paper, which we are now submitting to the journal Quantum, exactly on this aspect of the interaction of quantum and AI in both directions. Because what I addressed here is one aspect of using, if you wish, machine learning to improve quantum. And there are other aspects, such as using neural quantum states to analyze systems, to certify, and so on and so forth. And of course, there is the opposite direction, which there is a lot of interest from the AI community in terms of when we will have a quantum computer, what can we already be doing which will accelerate that. And there is a lot of scope for both, not only industrial, as you correctly said, but also, of course, academic research in this sense. And also on this, intersection quantum AI, and especially quantum machine learning, there is going to be another call for proposals from the European Commission, exactly trying to understand that. And actually what you were saying before, just before the talk when we were having this chat in terms of Gen AI, possibly being used for this purpose is, I think something which people have not yet thought about and could be very, very, like in the case of humanoid robots, as you mentioned, could be a very interesting development. So also scientifically, I mean, this is something which is at the center of attention, and it goes very much beyond the sort of the trivial idea, which is what I showed here, about using some ML or control stuff and just making my devices better. So there is much more depth in there, and there is a lot of appetite for doing that, I see, in the community, on both sides.
Thank you. So maybe for the meeting we can take into account this Spine's Heart monastery where we were last week. So this is a monastery near Bayreuth, so 1 hour driving from here basically, and half an hour, so I think it's 30 kilometers away from Bayreuth. It's an extraordinary place, and this is a facility that has been built by the government of Bayern. Precisely, it's a center of conferences and meetings and discussion with a focus on AI. It's part of the artificial intelligence agenda Bayern. So this could be a fantastic spot to meet to discuss all these things. So yeah.
It seems a great idea. And I also happen to be on the board of a foundation, the Heraeus Stiftung, which is funding activities in physics, and we have one channel of funding for Hüttenseminare, which means, a seminar which you do, like a retreat, either for individual groups or for cooperation. So this we could even apply for that in the next round, which is in a few months, and really plan for that. And this sounds like a fantastic venue, absolutely.
Yeah, so Spine's Heart is growing. So far the activities are developed in the old monastery that was totally renovated 10 years ago. So it's a fantastic place. But the space is limited in terms of, I think they have housing. We were like, how many? 25 people or so. I think is more or less the threshold. They are building new facilities. In 3-4 years, they will have other buildings attached to it. So the center will grow. But if we are thinking on a group of 25 people or so, this is feasible within the present facilities. And yeah.
Makes sense. My group is 55 people at the moment, so it would not be for everybody, but of course it's not something which would be relevant for everybody, so we would need to it would make a lot of sense to select a few people who would be especially suited for this. So that's, and honestly, it sounds to me the right size of people, okay? Because to have an initial conversation in which you really, is not just a conference or a workshop, but you really have a discussion, that's what you want to have. So that's fantastic. So maybe if we can be in touch, I mean, there will be some of your postdocs. I met Lorenzo before. There will be other people who could maybe help, and I will establish some contact with people in my group, and we could start sort of preparing this for, in several months. Indeed.
And then, and then try to keep it. And then, in this way, we can also try to do it in finite time, right? Meaning
yes.
Maybe finding a couple of days to go there in the spring or so.
Yes.
Not in 28, right? But
yes.
say, okay, 3-4 months from now, we can try to do it, and then we can go, I don't know, whenever it's more convenient, Thursday and Friday or something like this. We have, of course, to check because, the center is being very successful on attracting activities. We have to check availability, but otherwise, well, transportation is very easy. In our case, they even provided a bus. So the bus came here, they took us, and we went all directly with the bus, and then came back, so it's very easy. Otherwise, one can drive, it's 1 hour, and yeah. From Bayreuth, some people even took the bikes, so yeah. Okay, so Tommaso, again, thank you for your extraordinary talk, and keep in touch. Thank you.